And we're live. Hello, everyone. From the SFU Trottier Observatory, virtually, though, we are doing Starry Nights live. My name is Matthew Simone, and of course, I'm joined by my co-host.
Hi, yeah, it's me, Indra. You can also just call me Indira or Indy. But yeah, I'm happy to be here, Matthew.
It's been a while since we've done this together, hasn't it?
Yes, it's been quite a while.
Yeah, and of course, we are joined as our moderators, or by our moderators, Zach Padre Bursick, and of course, Kyle Daly as well. And so they're going to be hanging out in the chat, asking and answering questions. And of course, we have our Rask volunteers as well. And right now, it looks like it is actually clear outside, so that is good. I've got ourselves pointed right now at Arcturus, so that's what you're looking at if you're seeing us there in the chat and in the feed. That star is followed by the arc of the Big Dipper. We'll get into that later. I just had something I wanted to point it to in the interim. But the reason why we've got it set in one spot, we're not moving around right away, is actually we have a guest with us today. So we are joined today by a special guest. Thomas, why don't you introduce yourself and what brings you here today?
Yeah, of course. Hi, my name is Thomas Globular. I am a fourth year student at Simon Fraser University, and I currently work under Joanna Wu, who operates and manages the Trottier Observatory.
Awesome. And you're talking to us today about some of the research that you're doing on galaxies. And which I thought was exciting about this is that you've actually been finding that some of your research contradicts what we think we should be finding given the theoretical models that we've got. But before we get into that, why don't you do a little bit of a background of what your research is about?
All right. So my research is studying blue-centered galaxies and relationship between the color gradient of certain galaxies and, dependent on their position within the cosmic web. Specifically, whether they are within different, like thicker or thinner filaments. And recently, my project is effectively a continuation of a project, which tested a theory using a theoretical model of the universe, a big simulation called TNG. And the results that I've found using observational data has contradicted the simulated data in certain areas.
Okay, that's sorry, I'll let you go, Matthew.
Yeah, I was gonna say TNG reminds me. Whenever I hear that, because you were chatting a little bit before the chat thread started, and every time I heard TNG, I kept thinking of Next Generation for Star
Me
Trek
too.
fans out there.
Me too.
I was like, a TNG model? I'm like, this is great.
I did want to ask just before we get into it though, Thomas, can you talk to us about maybe your motivation getting into the field of physics, like how you found yourself here and how you found yourself working, for Dr. Joanna Wu and your special interest being astrophysics. How did you get here?
Yeah, of course. So when I was in high school, it was pretty much in that stage that everyone tends to find themselves in, where you're not exactly sure what you want to do with your life or where you want to go. Um, and it was actually in 10th grade physics class that I found that answer, where I had a student teacher who was quite young and very friendly and super awesome. And she actually had a degree in astrophysics herself. And I'd always been like fairly good with numbers throughout like middle school and my first year of high school. But something like astrophysics and physics, I guess as a whole, always felt like something that was reserved for the especially intelligent. And I never really considered myself to be one of those people. But meeting this teacher and going through her class kind of made that feature obtainable and reachable. And so since that point, I've pretty much just dedicated myself to that. I wanted to do as much as I could with the life that we have. And I figured that research and astrophysics as a whole was the right direction for me. And so ever since then, I've been studying and I continue, I plan to continue my research for many years still. But it's brought me here to now my fourth year at Simon Fraser studying physics.
That's
And
amazing.
Joanna was a professor that I had, and I had approached her about a project, and that's how I've started here.
Does that teacher assistant know that they had that impact on your life?
I don't think they do because I wanted to talk to them more, but I had never found the way to reach out to them. Though I did know, so I mentioned she was young. She was so young. One of my classmates was actually her younger brother. So she was close enough that I do have that connection at the very least. So if I suppose it's not impossible to reach out to one of my old classmates who at least we are familiar, and I could be like, hey, but I don't want to reach out to someone and be like, hey, so what's your sister up to?
I think it's important for educators to know the impact they've had on our lives, even after all this time, right?
Yeah.
For sure.
What I've done here, Thomas, I brought up an image. This is one of the first process pictures that we've done at the Trottier Observatory. It was taken by Dr. Howard Trottier, who started the observatory up, and it's of the Pinwheel Galaxy, so M101. It has a very distinct color scheme. So if you're looking at the galaxy, it's very blue on the outside. You have those magenta star-forming regions, and then sort of a very reddish interior. Now, when you're talking about blue-centered galaxies, are you meaning galaxies that would be different than this image that we're familiar with, is kind of like blue exterior with a reddish core?
Yeah, I mean the exact opposite, I suppose. There's blue-centered galaxies and there's red-centered ones. I actually have a couple images I could show.
Yeah, for sure.
Uh, if I can share my screen here. So here's kind of what we're used to as a typical red-centered galaxy, and it's pretty obvious that this one would be considered a red-centered galaxy. This is the M81 galaxy, which is a super popular and common galaxy for research. I've actually done work under it, or looking at certain properties of it,
This is one of my
using the chart.
favorite, Bode's Galaxy. It's beautiful.
Yeah, it's super awesome. And you can totally see the color gradient is super clean. And this is kind of the typical model of a galaxy. Because as the model of a galaxy typically says that we start from the inside and build outwards. And we fuel, new stars start forming on the outside. And so that's why we get these new, young, hot blue stars around the edges of a galaxy and these old, cooler stars near the center. But every once in a while, we also get other galaxies like this one, which is the NG1313 galaxy. And it's a bit different from our old one, where you can see it's quite blue near the center and a little bit more reddish, maybe brownish around the outer edges. So this is a good example of a blue-centered galaxy. And the question is, why do some galaxies form this way, where it actually accretes gas into the center of the galaxy, fueling the birth of new stars in its center rather than the edges? And the theory that we had been working under on a project that was done before my time was that it had to do with where in the cosmic web the galaxy lied with respect to one of its filaments. With the cosmic web being this huge, I've got an image of that here as well. So you can kind of imagine this is our galaxy here. It's this huge stringy web of information. But what's interesting about it is that if this is our galaxy, it's actually quite structured rather than just some big bunch of galaxies in space everywhere. And so this actually, the reason that the galaxy is structured like this web, with all this empty space in certain areas and a very big dense area space in others is, I mean, this comes all the way back to the Big Bang. After that happened, and the galaxy was this big, hot, chaotic soup of particles and energy and dark matter, or dark energy. What happened is that it wasn't exactly even, and there were random areas where there were maybe some gas that was slightly more dense than other areas of gas, and there were some that were quite light in comparison. And then over time, throughout the years, gravity and dark matter and everything formed into these. I mean, just over time, we get these big filaments, which are kind of like the threads of the spider web here, which connect these larger areas. And so the theory was that depending on the density of the filament that you were in, that actually had an effect on whether your gas would accrete into the center of your galaxy rather than the outskirts of it. And that would cause blue-centered galaxies rather than red ones, which is how we end up with phenomenons like this. But although I guess I shouldn't really say phenomenon because they're actually quite a lot more common than theory predicts. And we actually find that about 30 to 50% of galaxies are blue centered like this one. which is quite interesting. And so what I've found in my research is pretty much the opposite of what theory predicts causes these things. Um, the research that was done before myself was pretty much testing the relationship between the density of one of these filaments and the color gradient of a galaxy within it. Which a color gradient tells us whether a galaxy is blue or red centered. And so the using a simulation of the universe called TNG 100, and there are different versions of TNG, a simulated universe, which has to run on like supercomputers and several different CPUs to even produce these terabytes of data,
Uh,
which create big galaxies like this.
and we were talking
Yeah.
earlier. Do we? And is what are any of these running locally to SFU, or this is stuff external to the university that we have access to?
Yeah, it's external. These are run by other like research labs that have the facilities for these big computers. Technically, we process the data on a more local supercomputer. There's one up on SFU called Cedar, which I believe has recently been upgraded to a supercomputer called Fur. Um, so we have local supercomputers that allow us to process the data and run tasks on it so that we can actually figure out something. I mean, you can imagine how much information there would be in a simulated universe. Um,
And sorry, just to add into that, I don't know if you said it earlier, but from where are we getting this data from? I don't know if you mentioned this earlier or not, or I've because I'm confusing earlier conversations with what we're talking about now. So where is it that you're collecting all of this data from?
it's from like a more private group. I'm actually not even totally sure if I'm allowed to say or if
Ooh, it's
it's not
secret.
people that I've personally worked with. Um, but we effectively just have colleagues that work in these labs with the supercomputers that run these huge TNG simulations. And I mean, if you Google TNG, I believe that like they are a big company that can run these for you. And I can't exactly remember if it was like the TNG developers themselves that run this for us, or it's a different group that has the computers and runs TNG for us. Um, but that's where we effectively send them ingredients for a galaxy and they bake a cake for us. And then they send us the cake and we take the cake into a bunch of different pieces and extract information that way. But I suppose the interesting part with what I've been doing is I've been basically recreating the results of the simulated data using observational data. So from it's a real data taken and collected from galaxies in our own universe rather than a simulated one.
Okay. Um, yeah, just because earlier I think we had mentioned we were kind of talking about Sloan and the databases, like that are available to the public, and you were kind of emphasizing how important it is to have like these large databases. So I was under the impression that you were getting info or data from Sloan, but I guess you're getting it from a private group then, right?
Oh, the simulated data and Sloan are different totally different things. So yeah, the simulated data is something that a specific lab group does.
Right. Yeah.
That's not the data that I use. I use observational data rather than simulated, and the observational data comes from primarily the Sloan Digital Sky Survey, which is a huge worldwide collaboration of catalog of galaxy data.
Right, yeah, I should have specified I was asking about the observational data. Sorry about that. But yeah, that's pretty cool. And Sloan, you were kind of talking about how important it is to have like, a database like open to the public and stuff, and how um I think we had earlier ended off our conversation by saying like, oh, build more telescopes because we need to not share, I guess like what were you saying? You were saying that like the time is being divided by so many people, it's harder to get information and stuff like observational data from telescopes to use for research.
Yeah, so there are different benefits to using a simulated universe and observing a universe. But they both have the same problem where they take a bunch of time. When
Hmm.
you simulate a universe, it can take months. It's depending on how much you want and how complex you make the ingredients.
Which I guess is
Uh,
really a short period of time if you consider the epics scale and time of the universe.
Yeah, it is. It's
Yeah.
insanely impressive. Um, but the big issue with trying to take observational data is that there aren't enough telescopes. There aren't enough observatories, and the really impressive ones are either A, incredibly expensive to run for even an hour, or B, impossible to get yourself a time slot because there's already enough people willing to spend the money to use these big things. Um, and so when we want to collect big amounts of data like this, it's one of the big benefits of it is that we have things like the Sloan Digital Sky Survey and other big catalogs which is a collection of public data where researchers all over the world can share their information. And I think that's really important for astronomers because for how many research groups there are that want to study, all of the galaxies in the sky, there isn't enough time or facilities to just do it all. So
Right.
being able to find what you're looking for because someone's done it already, is a is a really big benefit. And it's what allows me to do my research because the data sets that I work with are like tens of thousands, if not hundreds of thousands of galaxies worth of information,
Wow.
which of course I couldn't go
Wow.
out and observe all myself.
So, Thomas, when you're saying that the observations are in contradiction with the predicted theory or what the theory predicts, what is that contradiction? So what is the prediction and what are you finding instead?
Yeah, totally. So the simulated universe. So one of the things that were compared with between galaxies' color gradient, so whether they're blue or red centered, and a property of the filament is the density of the filament and the color gradient. So the comparison they found is that there was actually a positive correlation between uh, dense or thin filaments and blue-centered galaxies. And so the simulated universe showed that typically in thinner filaments, there was a larger collection of blue-centered galaxies than in denser filaments.
Hmm.
But what I've been finding in my with the observational data, where we can measure both the filament density and, of course, the color gradients, is that we have the opposite correlation, and that in our universe, we actually have more blue-centered galaxies in the dense filaments.
Oh, wild. Okay.
There are other things that the simulation also measures. For well, like one thing that I can't measure observationally is angular momentum of the gas that's accreting through the filament and within a galaxy, which is very useful information because it kind of tells us more about physically what's happening. But for now, all we can tell is what color the galaxies are and the density of the filament that they're within. And so, yeah, it's really interesting how we're finding totally different things since the simulation is, of course, built off of mathematics that are, all theoretical mathematics that describe how galaxies are formed.
Yeah.
And yet finding the opposite result within a simulation that we find in actual observed data.
That's awesome. So like this I think this is really good too for people to understand how research like this is done and then ultimately also how science is done because if we don't have a predictive model, then we need to go back and figure out why. And I think unfortunately right now the way that science is depicted in popular culture in the media is that science and scientists is like a bunch of people in a building and they decide what we're going to tell the public now and then that's it. And clearly you're demonstrating that that's not the case, that if we have a misalignment between a prediction and observation, then we need to do something. So what is that something that research like yours would now lead to?
Well, now I suppose it goes into all kinds of things. We have to, of course, confirm that the results are accurate several times over and make sure that we're making, like now that we see that because it's easy if we found that the same result between observational and simulated data were the same, then it's a lot easier to take that and throw a hallelujah, throw your hat into the air and start writing papers about it.
Yeah.
When it's different like this, it inspires a lot more deeper research into the properties that actually do cause these things.
Yeah.
So now the question is, now where the question was could have been why are there more blue-centered galaxies and thinner filaments? Now it's why are there more blue-centered galaxies and thicker ones? And
Right.
so you get to explore all kinds of other properties that may have an effect on these kinds of things. You get to refine how your data is collected. We can refine how we determine the density of a filament because you can see that all of these lines here, all the webs are quite different from each other. So maybe there has to be more effort put into how those are defined and how we collect data that way. We also can use different catalogs. The way that color gradients are measured using in Sloan is different how they're measured in other like sky surveys, like something called MONGA, which uses a totally different method of collecting spectrographic data from galaxies, which is really cool, and I would highly recommend looking that up if anybody is interested in the. It's called MONGA, which is another sky survey. But of course, the downside of that is that it's fairly new, and now I go from having like 600,000 galaxies to only 10,000 galaxies with data.
Only.
Um,
Yes, only 10,000 galaxies.
well, it's a lot. It sure is a lot less though,
Yeah. Um,
especially considering just how many galaxies there are.
are out there, yeah, for sure. Thomas, one of the things, just to add context, because we've been on this particular image now for a bit, and I see some questions coming up in the chat thread. So when we're talking about the cosmic web and this particular picture that you're showing us right now, pretend we don't know what this is and someone has just looked at it. What are we actually looking at in this image? What is it depicting, and what is the scale of this photo?
Okay, this is pretty much as big as scales get. This is the structure of our universe. The cosmic web refers to the way that, you can see by the image appropriately why it's called the cosmic web. But this pretty much is our cosmos. It's insanely huge scale. We could be, I'm not exactly sure where in here we are, but I'm sure we are. Um, and it effectively this is how it's interesting because when you look up at the sky you see stars everywhere and you think that they're randomly dispersed somehow, and what the cosmic web shows is that there is a large and complex structure to our universe that you may not expect just by looking at it. The same way how if you're on a plane and you look at someone's lawn, it just looks like a big green patch. But when you
Right.
get down on the ground and in the dirt, you see that there are roots connecting the different blades of grass and the trees. And it's kind of, well, I guess that's on the opposite scale though.
but
But
but similar, right? So just in terms of like the density and the individuality of the objects that you're looking at. So
But in terms
like
of what you're
trees or
actually
forest,
what,
yeah.
what you're actually seeing here is all of these brighter areas are very dense areas. So these are where all your galaxies are, and then you can look at a patch down here or up here in the top, and you see that it's quite empty. And that's quite an interesting idea, is that there is a large amount of empty space in between all of these.
Hmm.
That's actually something that I wanted to point out was that like an image like this is really neat because you get to see like the hot spots, kind of like the city centers of galaxies, with these filaments. But then there's also, parts where it's just empty. And there's not a whole lot happening. There's not like it's dark. And I feel like that's kind of I don't know about anybody else, but to me that's very terrifying. Just empty, like dark space. And so it's not as, I guess, would it be correct to say that it's not as like as homogeneous as we thought it was, like
Absolutely.
certain
That's exactly the
spaces?
word I would use. It's non-homogeneous. It's
Mm,
it's not a it's not like like a cup of water where there's as much, if you look into a glass of water, there's water everywhere and it's somehow evenly distributed. There's empty space in here.
mm.
And I think it's really neat looking at how structured our galaxy is. I know I keep using that word, but I mean it's I think this is one of the most fascinating things about our cosmos is just how complex it's actually built.
And I don't know if you can answer this question, but I'm kind of reading the chat as well about people asking about blue-centered galaxies versus red-centered galaxies, and someone asked if the blue-centered galaxies would eventually become red as they age. So in terms of blue-centered galaxies and red-centered galaxies, is there a difference in age, or are they around like the same age, the ones that you're like studying, I
Yeah,
guess?
so we take a look at like an image like this, and we see that it's red in the middle and it's blue on the outside, and I mean the color itself does tell us about the age of a star. With the general like science or theory about how galaxies are formed is that you start from a point and you grow outward, and so you start growing stars around your edges. And so that's why, like, so older galaxies are redder. So it's kind of like you say, how like do blue-centered galaxies eventually become red-centered? I would say the answer is typically no, because what's happening is that a blue-centered galaxy, rather than forming stars around its outside, is it's actually forming stars in its inside and pushing the old ones out. And so that's why we get red on the outside, because those are the older stars that have been pushed out by the new stars growing in the center, like in this image. So like around the edge here, we have more red stars, and yet we have very bright young blue stars in the middle. Um, but you kind of imagine that if it's always growing blue stars in here, so yeah, all of these blue stars here will eventually become red, but the galaxy itself will still be blue centered because these ones are just going to get pushed out by new stars forming in the middle.
Okay.
So it's not going to become red centered, but the stars do, as they age, they do become cooler and they do become redder, but
Okay.
not red centered though.
Okay, I do feel like we're living in quite a exciting time for in terms of research within galaxy evolution and galaxy formation, because I know there's also albeit clickbaity titles and whatnot of things saying, oh, James Webb has found like even galaxies that are older than we expected them to be, and now we're finding an abundance
Supermassive
of
galaxies,
blue-centered
giant
galaxies.
planets.
Yeah, so it's really an exciting time to be researching this kind of stuff. I know we are running low on time for this. Matthew, did you have any like any final questions
Yeah,
or?
I'd one more thing. So Tom is if I understand correctly, you're doing your undergraduate degree right now. Is that correct?
Yes. Yeah, I'm just finishing my honors.
So
Hopefully within the next year here.
yeah, so that's amazing because
Nice.
normally, I would think of the progression of someone's academic career, being able to push back against like established theoretical predictions is something that'd be going on in like your master's or like doctorate level. But you're doing this kind of work right now, and in your undergrad, is that unusual for that to happen?
I it's kind of hard to say. There are some very cool projects that you can work on at SFU, which work on perhaps established concepts, but still have all the potential to discover new things. So another project that's happening at SFU that I had the privilege of working on was P1, the P1 collaboration, which is a particle detector, a brand new particle detector that is still being built right now by a research group at Simon Fraser University, and it's going to be built right off the coast of BC here. And that was a cool project because it was, it has the potential to discover new things and be used for that. But the work that I did while I was in development of the technically already exists. Um, and like the particle detectors themselves and the physics describing how to make those already exists. Well, although the engineering is really the new stuff of it. So to work on something like this, where it kind of is where it's so open-ended because it's something that we don't have the answer to yet.
Mm-hmm.
Yeah, I think it's really cool and an awesome opportunity.
Yeah, wow. It like
Amazing.
sounds like some cutting edge stuff. And it is really, really cool. Thank you, Thomas, for joining us. Looking forward to seeing you in person at our Starry Nights events up at the Trottier Observatory.
Thank you so much.
I also have Indra. So during the conversation, I brought up here, someone had mentioned in the chat that that the cosmic web looked like neurons.
Mm.
And like that is there is some similarity in that. So I have this picture here that kind of shows the cosmic web contrasted with neural connections in a mouse brain, and there was some research that actually showed that networks that are formed by nature and also by whether physically but also biologically on very tiny scales but also very large scales are similar to each other. So in a way you do kind of have a similar network in your brain as our galaxies in the universe, which is pretty wild when you think about it.
So, so Matthew, are you saying that we could be like in a giant mouse brain?
And
I'm sorry.
just running a wheel over and over and over
Yeah.
again on cosmic scales. Yeah,
Yeah.
it might be difficult to
No,
have
but
a
it's
thought with light years separating your neural information, but yeah, I guess so.
yeah. No, but it is fascinating. I saw that comment too, and it's something that I think is just I don't know, it's just fascinating. And I did want to ask are we what are we gonna be we can't look at stuff like this through the telescope, but we can look at other things. And so I did want to ask what's on the menu today
What's
in
on the
terms
menu today?
of
We have galaxies. We've got some nebulae. We got all kinds of stuff. So all of which I'm pretty excited about, and so we can start looking at stuff now. We have this big telescope that we could use to do that. Before we jump into that, though, you brought up one other really interesting topic, and I don't know if we wanted to jump into that first or go into targets first, because you wanted to talk about Atlas, this exocomet that's traveling through the solar system. So I don't know if you wanted to jump into that now, or do you want to jump into some targets first and go from there?
I do kind of want to look at some
Let's
targets,
look at
and
some
maybe we
targets.
could
Okay, let's
talk
do it.
talk about Atlas while we
Later on,
do
yeah.
some live stacking, you
All
know?
right, yeah, let's do it.
I'm
So
itching to see a nebula or
I
something.
yeah, we had so we wanted to start with some nebula. Well, I love that Thomas was talking about galaxies because we're going to get into galaxies later, and one of them was actually a galaxy that he already showed us, MNU1, Bode's galaxy. But let's start with Eagle Nebula. So there are some summer nebulae that are toward the south that are these awesome star-forming regions in our galaxy, not in the core, but toward the spiral arms. So we're looking toward one of those right now. So let's get ourselves set up here. So we're going to point our telescope. What you're going to be seeing here in a moment is the software that we use to point our telescope. It's called, well, it's a map of the sky that we call the sky. And so called. And it helps us to point the various directions in the sky. And it also not only turns the telescope, but also the dome of the telescope as well. So we've got some cameras set up. If you joined us before, you'll know what the routine, but we have a telescope internally that is showing our camera inside that's showing the telescope itself, but then also two cameras that are on the exterior of the dome that are showing the rotation of the dome too. And so what I'm going to do is find what's called the Eagle Nebula on the map that you'll see here. Are we looking at it yet? Why aren't we seeing that in the stream? Let's see.
Yeah, I mean the stream is a little delayed, so it's possible. Yeah, I think I'm on like a 20-second delay, but yeah, no, I was doing some proper research beforehand, like just trying to find some fun facts on the Eagle Nebula, specifically the pillars of creation, because I remember when I first saw them, it was just amazing seeing them, and then when I got to see the entire nebula, it kind of broke my brain that the pillars of creation were only a tiny part of this whole nebula. But upon, looking up fun facts and whatnot, there's debate as to whether or not they're like still around, the pillars of creation. I know that the Spitzer telescope, is that how you say it? Spitzer?
Yeah.
Alluded to the I guess it suggested with evidence that the pillars of creation might have been kind of blown apart with, just cosmic winds and stuff.
Supernovae and that kind of thing.
Yeah, but then at the end of the article that I was reading, it said that newer research is showing that there is no evidence of like supernova remnants within the pillars of creation, which would suggest that they're still around and kicking, apparently.
That's
But
awesome.
I mean, the light might not have gotten to us yet, as well, right? So, because how far away is this object?
It was the first space poster that I had in my house was the Hubble Space Telescope's image of the Eagle Nebula, which is 5,700 light years away. So if we're looking at it here in SkyX, I got it up. I had the wrong window showing here. But if you're looking now at the stream, you'll see that this is the software. So this is the sky. And you can see here is where the Milky Way is stretching across the sky. So we're looking south-southwest right now. This is toward the core of the Milky Way, and this is where that galaxy is looking toward, or sorry, where that star-forming region, this nebula, is toward the center of the galaxy. So I'll hit slew here, and we will move the telescope. You'll see a yellow circle converging with a red circle. The red circle is our intended target. The yellow one is where the telescope is actually pointed right now. And then you'll see this kind of contrasted sort of rectangular shape. That is where the opening in the dome is right now. That is now moving to where the telescope is pointing.
Perfect. I'm excited.
Yeah, hopefully this works. I will admit I'm a bit rusty. I haven't done one of these in a while, so here we go.
Me neither. There we go. Okay, cool. Yeah, I mean, like, did you have anything else to add about the Pillars of Creation or Eagle Nebula?
Yeah, it's one of our, it's a star forming region in our galaxy. So that's like where new stars are being born. So one of the reasons you might say, like, okay, well, you mentioned why would the pillars themselves, those actual filaments that are like, tens of light years long, be gone? And the reason is that while stars are forming in a region like this, while some of them are newborn, if the really massive stars that are created in these regions too, some of them burn up really fast. So some of them are actually exploding and dying while others are still being born, and the shockwave of that can wipe some of them out.
Okay.
This is really, really bright.
Okay.
I'm told my audio is a bit quiet, so I'm going to turn it up here a little bit.
Yeah. Yeah, it's interesting reading these things. I did take this information that I learned from Wikipedia. I don't know how much of a reliable source that is. But I was kind of shocked that the very end of the article, it just said that, like, it's still intact, and that predictions say that it's going to be like blown apart basically in like 100,000 years, I think.
Wow.
But yeah, pretty cool stuff. The pillars themselves are something called Bach globules. I don't know
Okay,
if I'm
cool.
saying that correctly. Bach is the last name of the person that kind of I believe discovered this type of cloud in space. But basically, these are Bach globules are basically like tiny, dense, dark, like nebulae. Or they can be dark. They're really dense, basically. It's just a dense area of cosmic dust and gas. And this is actually a great place for stars to begin to form. Great stellar nursery area for sure. Are we getting something?
Well, we are on target. Just kind of aligning our colors right now, so you can see me adjusting some of the colors in the histogram that determines like where the bias is in the different colors we're looking at. And let's see if we can bring out some of the structure in there. I know that we have captured this one before, but right now this target is a little low to the horizon, so we might be in a little bit of the glow. Especially if there's a little bit of cloud out there, it might obscure what we're looking at.
Yeah, there were kind of light, hazy clouds kind of going over earlier today. Yeah. Okay, well, I guess while you try to figure that out, I can yap a little bit about Atlas if that's okay.
Sure, please.
Okay, cool. Yeah. So I was talking earlier to my friend Kyle, who's in the chat, about just, asteroids and how it seems like there's been a lot more asteroids in the last few years, I'd say maybe like a decade or so, that we've been able to capture, and they're kind of, they're hurtling towards us. The one that is recently making headlines is an asteroid called Atlas, 3I Atlas. Um, and I think what was interesting is some people, like, I kind of asked myself, okay, well, why are we noticing these asteroids coming in? Like, it just seems like there's a lot more asteroids now that we're seeing, as opposed to before. And that's when Kyle made a good point that our technology is getting better. So these things were probably always happening, but we're getting better with asteroid hunting technology, such as telescopes in Chile and stuff. They're out there looking for asteroids. And so we're developing a lot more better technology to be able to capture these things and study them as well. Um, and this asteroid 3I Atlas, I keep saying to me it looks like 31, but 3I Atlas, I believe it kind of looks like a spaceship as well. I don't have the picture here, but
Yeah, I'm trying to bring up
um,
a sort of an artist rendition of it at the moment.
yeah. And I'm sure that an asteroid looking like a spaceship will be great for people that, believe in other things. Maybe it's a different kind of thing in the sky, the conspiracies and stuff. But yeah, it's pretty neat. It's just neat. I think there was another asteroid a couple years ago called what was it? Oumuamua, I
Hmm.
think.
Yeah.
Yeah. Um, and yeah, so it's just interesting that, we're getting to a point where we can kind of, see that stuff and whatnot.
Yeah, so I just to bring up, so it doesn't look like it looks like I've been told that the southern sky has a lot of cloud in it right now, so we might be looking through some of that cloud cover. I brought up an image here of Atlas, kind of an artist description. It might be significantly larger than Oumuamua. We're not exactly sure, but you're right. The cool thing about it is that this is an exocomet, so this is an object that has arrived from outside of our solar system. I think we may have only found 3 of these so far. You mentioned the shape of it and an alien spacecraft. Unfortunately, I'm not going to give this person. I'm not going to platform them by talking about their name or give them airtime. But there is a pretty well-known scientist who's been mentioning that this is, or very well could be, an alien spacecraft. But I used to write for a space news magazine called Universe Today. I really enjoyed my time working with them, and I remember our editor saying something really important when we talk about stuff like this: it's never aliens until it's actually aliens. So the importance of ruling
Yes.
out every other possibility first. And it kind of obfuscates the coolness of what it actually is. Like it could be up to 9 billion years old, older than our entire solar system, and this relic from an earlier time in the galaxy before our solar system was even here. And that in its own right is amazing, even if it's not an alien spacecraft.
Absolutely. I agree. Yeah, wow, the shape and size of it is a lot bigger than Oumuamua, which is a little jarring. So sorry to go back. So it looks like the sky is a little bit covered. I did set up some different um targets that are in different parts of the sky. I'm not quite certain,
We might need to
Matthew.
move to something more northernly, so maybe one of the galaxies. I just brought up here, if we are the sky software that we use, if we zoom in, gives us kind of a representation of the field of view of what the telescope sees. So everyone's kind of looking at a purple square right now. That purple square is the field of view of the telescope. So this is the view of the Eagle Nebula that we would have. The pillars of creation are this structure right here. And just in case this happened, I have another image stolen or borrowed, you could say, from the Hubble Space Telescope. This is actually a comparison of the Hubble Space Telescope and the Webb Telescope, and shows the difference between the two. So there's that zoomed in structure of the actual pillars of creation themselves. And the reason why these two look so different is that this image of the Eagle Nebula taken by the Hubble Space Telescope is primarily in visible light. And that light, a lot of it is obscured by the dust and gas of the nebula itself, whereas the Webb telescope isn't seeing invisible light. It's looking at infrared light, which can pass through dust and gas and allows us to see a lot more of these stars, especially young nascent ones that are being born inside of that cloud. So that's kind of a comparison between two much more expensive telescopes than ours that can see above clouds because they are in space, which helps when it's cloudy.
Yeah, actually, I did want to say, going back to the view of the sky, you could always show that we have that Trot Obs all sky cam.
Yeah, let's bring it up here for a second.
Yeah. But in terms of looking at galaxies, we did come up with a beautiful list of galaxies. A lot of them are northeast, so we could always look at Andromeda or Bodes.
Yeah, we can try Bodes. I have the All Sky camera up right now, so people are looking at it. So this is a camera that is on the top of the observatory. And as you can see here, looking south, which is where we are trying to see this nebula right now. There's a lot of clouds. And you might say, hey, we still saw stars. And that's true. The light from those stars can still penetrate the clouds, but the very sort of faint light of these nebulae is filtered out by that extra material in the sky and the clouds and everything else. So it's why basically the nebula is subtracted while we can still see the stars. So why don't we try one of those galaxies? Let's do that and see what happens.
Yeah, for sure. Sounds like a good idea. Yeah, I did want to kind of nerd out about the nebulae, different kinds of nebulae and whatnot, because I believe the Eagle Nebula is an emission nebula, and so emission nebulas are really interesting because they are basically made up of, and correct me if I'm wrong here, Matthew, ionized gas. So there's like nearby stars that are ionizing or exciting the gas around them, and it's causing them to kind of glow. But then there's other types of nebulae that are different, such as reflection nebula, which are usually they're kind of like, if there's stars that are nearby, like dust and clouds, and they're not hot enough to excite the gas or ionize that gas, then what we'll get is reflection nebula instead. So the light from that star, that cooler star, is just going to reflect off of the gases basically around it.
Yeah, totally. And in fact, one of the sorry, I'm still I was trying to leave you hanging there. I was trying to find stuff. But yes, you're absolutely right. One of the nebula that we're trying to show is the Trifid Nebula. It's actually an emission, absorption, and reflection nebula all in one, which makes it super cool. So basically, it will show all three of those different types. So absorption nebula are like really dark. Reflection tend to reflect starlight, where emission is giving off the light of its own. But yeah, absolutely.
Yeah. No, it's cool. I did want to see the Trifid Nebula. It had all those different regions. It also had the Bok globules, I believe, or maybe it was just dark nebulae. Sorry. I believe it was just dark nebulae, which would have been really cool to see, but that's okay. Because Bode's galaxy is absolutely beautiful if we're able to get a look at that.
Yeah, so we're shooting over to that right now.
Okay.
I'm told that one of my cameras is showing the news. That should be fixed now. Thanks for the heads up.
Yeah, there we go.
Listen, there's a lot of spinning plates doing one of these streams, okay? There we go.
Yes, I do feel fortunate that, Matthew is here taking care of all the technical stuff, so I appreciate that.
Oh, yeah.
It feels a bit stressful.
All right, rotating over. You might notice here, this is the Big Dipper. So you can see here in the screen, part of Ursa Major, and that's in the direction that we're looking at right now. It's possible that this is a tree. We might be looking into some trees right now, but let's see what we can find and if that will pop up on the camera. So we're going to clear, what we're doing right now is something called a live stack. So that's when we literally make a sandwich out of data. So we've got images that we're taking, they're 20-second exposures at a time. We're sucking in all that light into the camera, and imagine the camera being like a rain bucket where drops of water are actually photons. So as those photons are falling into the telescope and we have the telescope exposing with the camera is collecting, and each of those photons are filling up that bucket. So we have more and more and more light to make our image. That's what allows us to see these kind of bright, colorful objects in space, even though they are very far away, and we're just getting a drizzle of those photons by the time that they reach planet Earth. I can see, it looks like there is a core here. So we're looking at part of the galaxy. So we are seeing it in there.
Yeah, maybe moving the black level to the left might be.
Yeah, let's try to cut out some of the dark here. I'm also going to let's reset our color spectra. And let's see what we can do. There's a lot of blue there in that part of the sky.
Mm-hmm. Okay, so this is Bode's though, right?
It will be if we get it looking like anything, which is the galaxy Thomas showed us earlier.
Okay, cool. Yeah, I was just gonna kind of spit some fun facts about Bode's.
Please do.
Yeah, so this galaxy is about 12 million light years away, and a light year, just for reference, because I was just, I was just kind of Googling things today and researching and stuff, and I know the speed of light and whatnot. So, light is really fast, but I kind of forgot like how much, how many, like how long a light year is. So I Googled to see like how far across a light year is, and it's quite far. It's 9.5 trillion kilometers. One light year, because a light year is actually a distance measurement and not like, a distance unit. It is not a unit of time, as the name would suggest. So one light year is about 9.5 trillion kilometers. And this galaxy is 12 billion light years away. So 12 million light years away. So that's like 12 million times however many kilometers. It's really far away is what I'm trying to say.
So far away.
Yeah.
I mean, like the incredible thing about that, it looks like we're still struggling with sky conditions in this direction, unfortunately. But what I always found amazing about this is like literally while you're looking up into the sky, you're looking at the past. You're looking at the history, the memories of the universe as those photons are traveling across space. So when we see these galaxies, we're seeing them, like you said, millions of years ago.
Mm-hmm. Yeah, no, it is quite interesting, and that's kind of why I was a little bit confused when I was reading about the pillars of creation, because data that we would be getting now, I was under the assumption that we would be receiving data that's kind of in the past technically, right?
Yeah, totally.
So I was kind of confused as to, how you can make the assertion that they haven't been just destroyed yet, basically, because we can't see in the future. We're looking into the past, so I feel like it's interesting. Studying space is really cool. It's like studying the past sometimes, right? Because you're looking at these objects and they're coming at us from millions of years. The light is hitting us from like millions of years ago.
Right. Yeah, absolutely. And basically, yeah, looking backward in time. That's one of the things about Webb and looking back at other galaxies, kind of like Thomas was seeing as well, is that you're looking at part of the history of the formation of the universe. There is a warning that I'm getting here saying that our frames are not stacking. And that's primarily because when we put all the stacks of the images together, they need to see enough stars in order to do that. So it's possible that we're not seeing enough stars in this direction of the sky. This might not be the best direction to look at. We can
Why don't you
try a different direction.
Did you uncheck align frames?
I have, yeah. So maybe it'll allow us to kind of freely stack. But I know that I have looked at this galaxy before, and we've been able to get more detail out of it than we are right now. So it's possible that we might be looking through some haze. We can't see the core of it, though. It is there.
Yep.
And thankfully, Thomas did show us this one earlier, so at least we know what it looked like.
Yeah. Well, let's, talking about the size of it, it's about 90,000 light years across. So it's pretty big. Pretty big. It's very bright, in terms of galaxies. And it contains about 250 billion stars, I think. So a lot of stars.
Amazing.
It's pretty big. Absolutely beautiful to look at through the telescope, when the conditions are well.
Yeah. So because we're kind of fighting right now with sky clarity, why don't we pick something that might be easier to actually find than a galaxy and go with, I know we had a star cluster on the list for today. Do you want to skip some of the galaxies for now and maybe get to the Hercules globular cluster?
Yes, absolutely.
Let's do that.
I love the Hercules globular cluster. It is so beautiful through the telescope. Seeing it even just through the eyepiece is quite a delight. So I'm excited.
Me too. Let's see what we find.
But yeah, just some information on the Hercules globular cluster. It is a very, very old cluster. It's about, if you round it up, 12 billion light years, or sorry, not light years, 12 billion years old.
So old.
Yeah, I mean, Matthew, how old is the universe as we know it?
13.8 billion years, as far as we can tell. So these clusters, and there are, I think, about 250 that orbit around the outside of the galaxy, are ancient blobs of very old stars from the beginning of the galaxy.
Yeah, and this is like another area of active research is star clusters, because I believe they're pretty stable, which is good for us for, aging them and whatnot. But they're I know that they're an area of active research as well. I am blanking on why. Matthew, would you happen to know why?
Well, I know that we're trying to figure out where they came from, right? Because these things are really old.
Right, yeah.
When stars are forming, so there's a couple different versions of clusters. Open clusters are ones that would have formed. And I wish this is why we could have seen the nebulae earlier. But when we were looking at, say, like the Eagle Nebula, that's where new clusters of stars are being born. They start as open clusters, and then they spread out through the galaxy, kind of like birds leaving the nest. They've just been born, and as the galaxy is twisting and turning and stars are moving, they spread out through the Milky Way. And so the cluster of stars that we were born in is now spread out through the Milky Way, and they have changed. And so I think we found one recently that is near us that might be chemically similar to our sun. So that might mean that it might have been born in the same cloud of dust and gas as ours. It's kind of like a sibling star. But these clusters always stay together. They are gravitationally bound, and so it's like a blob of stars, or a glob, so-called, as they are globular clusters, that don't separate apart. And I think that there is some debate as to how they formed. If I understand correctly, one of the main reasons we think that one of the main drivers of the formation of these star clusters is when galaxies collide. And when those collisions happen, you have these massive knots of gas that come together and form these huge clusters of stars. And because there's so many that form so quickly in such a close area, they are stick together, and so they never really separate. And so they might be from those early times when our Milky Way was still forming with other galaxies.
Oh, okay. That's awesome. Yeah. So I do. Yeah. So I also wanted to ask. I don't know if you know anything about this, but because we have globular clusters, like these huge clusters of stars. Like what differentiates like a globular cluster such as the Hercules as opposed to like a galaxy or something? Because I feel like after time, like it would eventually become a galaxy, or am I wrong?
So they themselves might have a few 100,000 stars, whereas a galaxy itself has billions of stars. So this might be a blob of a larger galaxy, but it's not, say, a dwarf galaxy, which might have millions and millions and millions of stars. And we do have some of those around our own Milky Way. We have two giant clouds of dust and gas that are also forming stars, orbiting around the Milky Way. They're kind of like moons of the Milky Way, and they're called the Large and Small Magellanic Clouds. They are primarily only visible in the southern hemisphere, so unfortunately we can't see them from up here, but we are able to see them. And there is one star cluster, or one globular cluster, that we do see in the southern hemisphere as well. It's called Omega Centauri. It is the largest and brightest of the known globular clusters, and it's possible that that was maybe the center of a smaller galaxy that we absorbed. So that it is possible that that might be the case. And so we see these big groups of stars, and they might be formed by the collisions of galaxies or stripped away from other galaxies by the collision with them as well. And I know that we had, for a while, there was a kind of ongoing conversation within the staff at the observatory as to what a sky would look like if you were inside one of these clusters. And so the stars are very, 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 very close together. And so it was kind of like saying, okay, would it look like day? Would it look like nighttime? Suffice it to say, it would kind of be like a very light polluted night sky all the time. So you would never really have a very dark sky. And this was talked about with Isaac Asimov, the famous science fiction author, wrote a short story called Nightfall that is about a civilization that's inside one of these clusters that don't know that that the universe exists because they can't see it. And they don't see it until there's a random alignment of a whole bunch of moons that covers the nearby stars. And for the first time, the civilization is able to see the wider universe. And I think about how much the view of the night sky has driven our scientific advancement. Imagine if we couldn't see it. How would we be different? How would you and I be different?
Yeah. I mean, I not just that, but also I do like learning about like different cultures and their interpretations of the night sky as well. So it's like, and like it's formed like different like stories within those cultures. So seeing the night sky and being able to see it is definitely, I guess it's kind of a gift if referring back to your science fiction novel, it's definitely a good thing. We would definitely be different. But also, I just wanted to say that shout out to Joanna for doing the math on that, because she did some math on what I believe the luminosity or brightness would be if you were like on a planet orbiting around close to the center of this globular cluster, and it was I didn't really know like you could do that, I guess. So it was really cool to see the math on that and stuff. And I know that I was for sure saying that it wouldn't be night ever. So I'm glad that we can kind of go back and revise these things and stuff,
Yeah,
kind of,
that was my understanding as well, is that inside one of these clusters, it would be almost more brighter, like dawn, or something similar to that. But so it is darker than I thought it was. So it was kind of one of these things where I was like, oh, that's what my understanding is. But it's amazing that you could actually go and make that calculation. So it's cool that we were able to figure that out.
Very cool.
Even though it's so far away. And this cluster in particular is one of the few places in the universe that we've actually sent an intentional message to. So we have sent a message to the Hercules cluster. It was from the Arecibo array, which is now collapsed, unfortunately. And it was more of like for fun. I can bring up the image here of what we actually sent there. It's called the Arecibo message.
Right, yeah, I'd forgotten about that actually.
Yeah. So here it is here. You can check out the Wikipedia article. So here is a visual representation of the data that was sent. So here's the dish below down here. And that's trying to show the actual dish that sent it, or a visual representation of that. This is supposed to be a person. Here at the top is a representation of our solar system, so the number of planets and their like various sizes. And down here is a representation. So there's the sun, and where we are is the one that's like raised up here in the picture. Of course, it's not going to get there for what, 30,000 years? Is that how far away that cluster is?
Round it up, yeah.
Yeah.
Like, well, yeah, and like, it is 22,000 light years away, so it's and we're not
Oh,
tra it's not
22,000. There you go.
traveling. Well, it's not. Yeah, it's not traveling nearly close to the speed of light, so it'll probably take. I feel like 30,000 is a much better guess. I've never seen the image before. That's really cool.
Yeah.
Very interesting.
And we have also processed an image of Hercules from our telescope. So that is an image of it through right now from like a few seconds of exposure time. But if we look for a completed image of it, it looks like this. So here is a fully processed out image of the Hercules cluster from the telescope. And you can really get a sense of just like how densely packed the star system is. And I saw it come up in the chat. I think Kyle already answered this question, but there was whether or not planets could exist in a cluster like this. And likely there's so much gravitational interaction between all the planets that those star forming dust clouds around them are just pulled apart by the gravity. So maybe no one can live there. Maybe you have to come afterward. Maybe as another civilization, then you come and set up camp in one of these clusters. Who knows?
Yeah. Sorry, because there's a slight delay. I am just looking at the image that we took at the Trottier Observatory.
Yeah.
It is beautiful. I love getting a like, there's so many different stars and they're all like different colors and whatnot too. Matthew, why are there different colored stars? What's happening there?
Yeah, so it's this was a mystery to us as well because in a cluster this old, most of the stars should be fairly ancient. So you're looking at stars that would only last billions and billions of years, so they tend to be lower mass stars. Ours is one of them. Our sun can last for probably about 10 billion years of time before it runs out of fuel. So don't worry, we're not going anywhere anytime soon. But we have seen in these clusters blue stars, and those stars typically tend to be younger or more massive, which means that in a cluster this old they should have burned out already, and so it's kind of a mystery as to why they're there. So the best guess we have is that these are objects called blue stragglers, and they're created by the merging of older stars. So it's when these old stars collide with each other in the cluster, all the hydrogen that's left over inside of them can kind of remix, and they basically create a newer, younger star, like a refreshing of a star. And this, in clusters like this where the stars are so densely packed, that might be one of the places where stars do collide more often, as in the rest of the galaxy that actually doesn't happen very often. There's most of the galaxy, for all the stars that are there, is mainly empty space.
Right. Is it possible that some of these young stars would be also formed just like you said, colliding, right? Like colliding stars?
Mm-hmm.
What about like some stars that like die out eventually? Like, so I don't know if any of them have gone supernova in our time, but I know that like because stars are like can form out of different nebulae regions and whatnot. They're kind of
Sure.
known to be stellar nurseries and whatnot. So is it
Yeah.
possible that some of these younger stars are forming from the nebulae of past stars?
Some of the stars that have died out, yeah. That's a good question. I don't know off the top of my head. My guess would be, and Dr. Joanna Wu could maybe weigh in here in the chat. My guess would be is that because of the same gravitational influence that would prevent planets from forming in a cluster like this, is that there'd be so much gravity that it would also pull apart the planetary nebula that are forming from the dying stars and preventing them from coming together to form new stars. That would be my guess, but I could be wrong.
Okay. Very cool.
All right.
Yeah,
Did we-
if Joanna could, I just thought about that too. Like, so I didn't get a chance to do any prior research to that, but it is really cool. I think this is, why they're like such a hot area of research right now as well, right?
Yeah, totally. Yeah, they're very, very cool. And one of my favorite objects to look at, not only in the telescope, I mean, look how pretty that is, but also in the eyepiece, because they show up so clearly in the eyepiece. It's like a cloud of fireflies. Maybe we could try another galaxy. We had one here that we could also try out, the fireworks galaxy. I'm worried that the clouds. Let's look at what the clouds are doing right now. What's going on? I've been told that the clouds might now be moving over top of where our nebula, or where our star cluster is right now. Yeah, we're starting to get patches all over the place. Okay, well, let's try one of these other galaxies. We had the Fireworks Galaxy on the list, unless you have another one that you want to check out beforehand.
No, I think Fireworks Galaxy is a good way to go.
This is was one of the first objects I ever tried to image on at the observatory.
Oh, that's very neat. I know that I definitely show students and anyone that comes in during workshops and observatory tours the image that you took of the Orion Nebula.
Oh yeah, yeah.
Um, it's also another beautiful image that you've taken. I'm just trying to load up the sky, what the sky is looking like. To see, because I did try to make a conscious effort to pick targets that are in different parts of the skies, because I thought, it's going to be 10% cloud coverage. Um, oh yeah, it's looking a little patchy, hey?
It is looking quite patchy out there,
Okay. I wonder if there's any, maybe we can look at if this one doesn't work, we can always try to look at a binary star system or
yeah. Sure,
something as
yeah,
well.
totally. It's one of the things I'm trying to fight for holes in the sky.
Yeah.
All right, let's see what we got. All right, cleared the stack. Let's try again. Still some motion in there. You can see this streak. It's probably from the telescope still moving, or something flying through the frame. One of the problems about all the satellites that we have flying around in space right now is they're starting to make observational astronomy really difficult.
Yeah. Um, yeah, that's something that's I've talked I was talking to one of my family members about that earlier actually. Because he had seen something in the sky and I just had to tell, he was like, "Oh, what is this?" And I told him like, "Oh, it's probably just, satellites passing over. There's a lot of them now
Yeah.
compared to like, 20 30 years ago kind of thing." So,
Thousands and
um
thousands. Yeah, actually, when we were doing Starry Nights last Friday, there was a chain of Starlink satellites that flew overhead. And those satellites, and we call it a mega constellation of satellites, but there's so many of them in the sky right now that not only are they blocking the field of view in optical wavelengths of light, but also they're just giving off a ton of radio pollution as well, which makes it more difficult. And I know astronomers have been trying to work with SpaceX about making those satellites less disruptive to astronomy. There's been reluctance. I think the company wants their satellites to be seen in the sky.
yeah.
We can
So
see
is
it. I've got
this
I see some structure. There's definitely, we see the core and some of the spiral arms here around the outside.
yeah. Let's see. Do you have any fun facts about this galaxy, Matthew?
Well, like the other galaxies we see in the sky, it's very, very far away. So Fireworks is about 25 million light years away, 87,000 light years in diameter. But one of the reasons it's called the Fireworks Galaxy is that there is, we've seen a number of supernova, like a frequent supernova going off in this galaxy. But also it is a starburst galaxy in that it is going through, at least 25 million years ago, an intense period of star formation. So usually when we call a galaxy a starburst galaxy, it might be creating stars at a rate of 5 to 10 times more than our galaxy is. And so that's quite a bit. Our galaxy makes I think anywhere between maybe 5 to 10 stars every year, so it's not a lot. So a galaxy like this would be making more of them, maybe because it has recently interacted with another galaxy. Maybe it's causing the gas inside to get stirred around, and you might have more stars being made that way.
Oh, okay. And I've also I've also heard that there are like kind of big voids in this galaxy as well that are quite significant.
That's awesome. I was not aware of that. I know there are large spaces. We actually might be near a large void where there's no stars in our own galaxy. So there, like in every galaxy, you're going to have these kind of like cavities where there's maybe not anything floating around. Maybe just like in the cosmic web, as we saw earlier, we have these voids in them as well.
Yeah.
Let's see.
Yeah, I'm starting to see some of the structure there as well. Um,
I can see some of the arms here. I'm trying not to cut off too much of the this glow here on the edge is probably light pollution. So you can see this kind of purple haze over here. It's probably light that might be coming from somewhere on the campus. One of the things that we've noticed is there's a lot more light on in and around the observatory since we first built it, just as the campus is developing. But one of the cool things about that is that a lot of the neighboring projects have started working with us in terms of helping to control their light. We've been given access to some blackout curtains that are on in the academic quadrangle, some of the buildings neighboring the observatory. So there's a collaborative spirit at the university to ensure that we're not getting too much light pollution into our telescope.
yeah, it's awesome. Love to see the teamwork and whatnot. Because I remember at one point Kieran, who's another staffer, who had 3D printed some light blockers to put just to dim the light a little bit, so that we can have better viewing conditions and stuff. So it's nice to see that we've gotten to a point where we can kind of collaborate and work on it together.
Yeah,
Because this is a very important part of the university, in my totally unbiased opinion.
absolutely. Yeah, I mean, it's an amazing facility. I was out there. I remember the times being out in that spot with Howard and his class when he was still bringing his own telescope from home and just setting it up in grass, like on a grass field,
Wow.
before we even had it there. So that's pretty amazing.
Yeah.
So yeah, on this telescope or in this galaxy, like you might have seen, we're seeing some of them at different angles. So when we saw the Bode galaxy, the one Thomas showed earlier, it was kind of on an edge. Whereas this one, we're looking at it kind of straight down from the top. So this is the core of it here, and here are the spiral arms. So we're basically looking at it from the top down or bottom up, if you prefer. So it gives us kind of this view of the whole structure of the galaxy. With the time we have left, do you want to try? You want to try Andromeda and see what it looks like?
Yeah, let's go for it.
All right, let's do that. And I know my understanding is I haven't been a part of the more recent project to image the Andromeda Galaxy, but I understand that we're trying to do a mosaic of the whole thing.
Yeah, and this has been like an ongoing project basically throughout the summer. A lot of the staffers and stuff are coming together and just taking images of. I'm not quite sure if it's like actively different parts of the galaxy, but just trying to create, yeah, like a mosaic. And the reason why we have to create a mosaic in the first place is because the telescope is really powerful, right? So when we look at Andromeda, we don't actually see it in its entirety. Am I correct with that?
Yeah, totally. So I'm trying to demonstrate that exactly what you're saying now. So if we take the SkyX, that software we use to point the telescope, and we zoom in our little field of view box, we see that Andromeda is so close to us, it takes up so much of the sky that we're only able to see a piece of it at a time. So in order to image the entire thing, we have to basically like take a mosaic, so to image different parts of the galaxy and then assemble it together. And so the galaxy is huge. Like if you could see, you can see Andromeda with the naked eye in the sky. It's one of the first objects that it's actually one of the earliest memories that I have of space is my grandfather pointing out the Andromeda Galaxy in the night sky at the cottage that he had. So it's this fuzzy blob, basically looking at the core of the galaxy. But if you can see the whole thing in the sky, it's like 6 full moons across. It's enormous, and so that's why it's required of us to do, given the field of view of the telescope, different images to put it all together. And right now we're kind of centered on the core. And so let's see what it's actually picking up. Oh, yeah, there it is. That is bright.
Yeah, I do like to say Andromeda is very huge in the sky. It's kind of like a mixture of Andromeda being really big and then also the telescope being super powerful. Because if you have
Yeah.
other telescopes, you can see it in its entirety. Like if you have like a hobby telescope or something, right?
Oh yeah, totally. Or even like a really good telescope that just has a wider field of view. So our telescope is enormous, as everyone has seen, and so when you're coming in and looking at it, we have a narrower field of view than someone might have with another telescope, and so that's why it takes up so much of the space. Let's see. I wonder if I can. What we'll do
And
is I'm gonna shove the telescope over a little bit and see if we can get more of the spiral arms.
oh, I'm starting to see faintly something.
So I'm gonna restart the shot.
Um, Yeah, so I believe, and is Andromeda the only object that we can see that is outside of our galaxy when we use our naked eyes, kind of? Because I know that all the stars, when we look up in the sky, all the stars that we see are stars within our galaxy. But because Andromeda is, so close and so large and, bright, um, with good uh, visibility conditions, we would be able to see it, and that's one of the only objects that we can see that is outside of our galaxy with the naked eye. Am I correct with that?
I believe that is correct. Yeah, and that's a really good point because I know when we're at the observatory and we're showing people stuff, that's one of the questions is like, hey, are what we are looking at right now in our galaxy or outside our galaxy? And that was a huge debate, right? For a long time, we didn't know if the Milky Way was the entire galaxy or not, and it was distance calculations to Andromeda that allowed us to realize that that this was an object outside of the Milky Way. They used to be called if I'm right, it used to be called the Andromeda Nebula. So we thought that maybe it was a nebular gas formation inside of our own galaxy. Just a quick note here: this is a satellite, so you see this zip right through the picture. Even our telescope, like we are impacted by space stuff flying around in space. So this is something we need to be worried about in the future. But yeah, exactly. We had to, and we've done this here at the planetarium. We actually tried to replicate Edwin Hubble, who made the calculation, although using research from a woman named Henrietta Swan-Leavitt, very important astronomer who helped to realize that there were ways that we could use specialized stars called Cepheid variables to measure distances across space. So she unlocked that capability that then Edwin Hubble then used to make the first distance calculations to the Andromeda Galaxy, which were way off, but enough to tell us that it was outside of the Milky Way. So he measured Andromeda at a distance of 900,000 light years. We now know it's closer to about 2.4 million. When we did the calculation ourselves, we got about that number. So, but we were also using a much more advanced telescope than Edwin Hubble had access to. Actually, in anticipation of that conversation, I downloaded here. This is one of the photographic plates that Edwin Hubble used to do this calculation. I'll zoom in here. So here is one of the plates. So there's Andromeda, very similar to actually how it looks right now in our telescope. And you can see Edwin Hubble's writing here that says var. What that means is variable. So him recognizing that variable star, or several variable stars that he noticed were in Andromeda, and that he would be able to use them to make that distance calculation, thereby ending the debate as to whether or not the Milky Way was the entire universe. And I tried to image Andromeda myself, so I'll bring this up. This is not the mosaic, so I'm looking forward to this, and I haven't been a part of that project, so I'm really excited to see that one. But this is one of Andromeda that I did, so this is fully processed after about 5 hours of image time and then a lot of processing. But when I centered the image, I wasn't looking for any one particular part, but Dr. Howard Trottier noticed that based on the angle I selected, one of the variable stars is in the picture, and it's this one right here, so it's circled. So this star is actually in Andromeda. That's one of the variable stars in Andromeda, and it's one of the stars that was used to make that distance calculation to the other galaxy. So this is one of those key objects in space that allowed us to realize that our universe is a lot bigger than we ever thought it was.
Very cool. And yeah, that was you had mentioned that you had recreate like at the observatory, some of the staff had like recreated that the I guess I don't know what you call it, like calculations or whatnot. And the paper for that was actually published. Am I correct with that?
Yes, yeah, it was, yeah. And so it is on the Trottier Observatory website. So if you go and check it out, it is one of the scientific publications. Several people from the observatory are involved in that. And we showed how we redid that calculation, Edwin Hubble's calculation to the Andromeda Galaxy. And one of the ways that we know how far away things in space actually are. So when we look at things like the maps of the sky or the Sloan Digital Sky Survey that Thomas mentioned earlier and that you mentioned as well, how can we build a map of something, of places we've never been to? It's like when people say, how do we have a map of the Milky Way? How can we have a map of something that we're inside of, or things that are so distant? And that is why we can measure the distances to these things. We see them, we add them to our three-dimensional models of the universe, and that helps us to know where we are in our place of space.
Yeah. It's kind of it makes me think of like, people that would explore around planet Earth and trying to kind of map out like where the land is versus where the water is
Totally,
without
totally.
being able to see like, Earth from space, which, eventually over time we got to do kind of thing.
Yeah.
It's kind of similar, I think, right?
Oh, I totally think so. Imagine like it's hard to imagine now that there were times when we didn't have a map of the Earth. That the Earth was as mysterious to us as maybe like the depths of space. I think that's so cool, and that people were exploring the first, maybe you've been the first person to be at a different part of the world, like no one had ever been there before. It's pretty amazing.
Mm-hmm.
All right. Let's see. We've got a couple minutes left. Do we want to try something else? What do we got left?
Yeah, I couldn't off the top of my head think of any binary star systems. And my I am limited in terms of my technical capabilities. Actually, let me see. I do have a phone with me.
How's our sky doing right now? No, it's I think even a little bit cloudier out there than it was before. Again, this is why we put telescopes out in space.
Yeah. It's no atmospheric disturbances.
None. Anyone have a favorite object they want to check out? We can go back to Arcturus because I can talk a little bit. That star is kind of cool. I can talk about it a bit if we want to do that. Because we had it earlier, but we didn't actually give it a conversation.
Arcturus.
Yeah.
Yeah, I think...
you mentioned Omicron Cygni. There was one, it had different star colors.
Oh, right. That was on the list. Yeah, we could totally look at
okay, let's do that.
Omicron Cygni, the colloquially dubbed the hockey stick star system, I guess.
Yeah.
Yeah, that one's about 1,100 light years away.
Wow. Okay.
And it's pretty neat just seeing the different star colors and whatnot. Especially if you're viewing in person, you can see the different stars and star colors just within the eyepiece. And it's just really neat to see because, once you kind of know, the orange ones are a little bit more cool and the whiter, bluer stars are a little bit more hotter and younger. It's really cool to just kind of just by looking at this star I know or the system I know which ones are younger and which ones are older. It's kind of really neat.
All right, so just moving the telescope. I love the terms of these stars are fun because they sound like science fiction-y space designations. There's reasons for those. So Omicron Cygni means that it is a group of the stars in the constellation of Cygnus. So here you can see we're pointing at Cygnus. This is the swan. So this is the tail of the swan. Here's the head of the swan. These are the wings here within the constellation. So that is why things have these names, because we're locating these stars within these various constellations. So let's see what we get. If it's bright enough, we might not have to use the stack, and we can do a live feed instead, maybe. Let's see what happens. Oh yeah, look at that. Oh, that's really cool because you can see some really distinct differences between the colors of these stars. Do you want to talk about star colors?
Yeah, I mean, I feel like, you kind of hit the nail on the head earlier, right? So the star colors, we know about the ages of the stars, judging off of what color they are, because their color gives off the surface temperature. Like the color tells us the surface temperature of the star. So older stars tend to be a little bit more red, red orangish. And then the older ones are, bluer white. Um, and it's kind of funny because Joanna had pointed out to me when we like have our tap faucet, for example, the tap faucet at home, usually blue signals like cool water,
Mm.
whereas the red part signals or tells us, hot water. Um, but in space, it's like the opposite, right? So in space, with sorry, I probably got that backwards. But in space, it's backwards. So the bluer, whiter stars are a lot hotter.
Hmm.
But the red, orange stars are cooler.
Yeah, totally. Yeah, so you think about that. It's kind of like with flame, right? When you have like a blue flame, and everyone's like, "Oh, this is actually hotter," which is wild. In this case, like one of the bluer star that we're looking at here in this picture is like much bigger and brighter and more massive than our sun. So this star is about 9 times the mass of our sun, which is amazing. So also why like usually these bluer stars tend to be more massive than our sun, which allows them to burn brighter and hotter. And whereas most of the stars in space, this is always wild for me to think about, most stars in space are actually red, but we don't see them because they tend to be fainter. And so if you do see those red stars in the sky, like Arcturus, the one that we saw earlier, and right after sunset, there's a very bright star right now in the southern, in the direction of the southern sky toward the southern horizon called Antares. And so if you do see red stars, they are red supergiants or red giants, these stars that are near the end of their lives, as opposed to the red dwarfs, which we don't see. In fact, the closest star to our own is Proxima Centauri. It is a red dwarf star, but we can't see it with our eyes. You need a telescope in order to see it.
Oh, very cool.
Well, this was cool.
Yeah, this was a lot of fun.
It was a lot
I
of fun.
think, we overcame the battles of nature.
We did.
The clouds and whatnot. I think we did our best with it.
I think so. Yeah, sometimes you never know, especially when you're not there and you're scanning the sky with a camera. It's difficult necessarily to know where you're pointing. But we did good. So thanks everyone for sticking around with us. Thanks as well to Thomas for coming on the stream and chatting about his research. So maybe we'll have him on again when he's further along and found more discoveries. It's so cool to meet people this early in their career who are challenging prediction, right? And that's how science works. And so that's how we come to consensus and learn about things. It's not like we're making up ideas out there. It's so much work. So people like Thomas looking at simulations, looking at observations. So all these things we know about the sky, it's important that we don't take them for granted. We need tools, we need researchers, people who are passionate about it, and maybe because someone, as he mentioned, has inspired him, and so now he's gone and maybe found some new discovery about the universe, and that's how everything around us happens, right? So it's people take that passion, that interest, and then wrestle with it, and maybe you have negative results at first, but I think we need to really appreciate the people who are doing research around us, and like Thomas said, he thought maybe he wasn't good with the numbers. I certainly thought that. I know I'm not grounding up the research, but I'm excited that I get to talk about the results of it, and sometimes meet those people who are, which is cool.
Yeah, of course. Thank you so much for having me
Oh,
on.
you're still here. Hi, Thomas.
Yeah, I'm still around. Sorry.
That's cool. I did. Thank you for sticking around to the end.
Love to come back whenever we have some more interesting results.
Yeah, totally. Sorry, I didn't realize you were still on the call. Well, hello, Thomas. Thanks for being here again. Indra, thanks for joining me as well and being my co-pilot here tonight. And then thanks to everyone in the stream. So Kyle, Zach, Dr. Joanna Wu in there as well. And of course, all of you for joining us for Starry Starry Nights. You know, we really appreciate everyone who joins in, especially live on the nights of. It's really cool to know that the observatory has this community of nerds who are all into this stuff, and certainly it's exciting for us because otherwise, we would just be talking to ourselves. So thanks for being here and sharing the sky with us. Remember that if you want updates on when we are running the observatory, you can sign up to the mailing list. You can get that link on the Trottier Observatory website, so it'll tell you whether or not we're going to be open on a given Friday. We also post on social media, so we'll post it on Twitter/X and also on our Facebook page, so you can find information there as to whether or not we're going to be open. Usually we make that announcement on a Friday afternoon between like 12 and 2 p.m. So we aim to be open every Friday, but it does depend on weather, so make sure you check those announcements, and then you'll know whether to be around. And then, of course, the last Friday of every month is a Starry Nights Live like we did tonight. So all the other Fridays are in person at Burnaby Mountain, Trottier Observatory. Otherwise, we'll be online here at the website or on the Facebook, the YouTube channel, where you are right now listening to us. Well, thanks, everyone. Have a great night, and we will see you again.